In this problem, we have a beam that is subjected to two linearly distributed loads. The first one from here to here, the second one from here to here, a concentrated force, and a free couple moment. And we need to first replace this applied force moment system by a single force, single moment acting at point O. And then for part B, we need to further replace that by a single force and specify its location. So the first thing you want to do is to replace the distributed load with concentrated forces. So for the first linearly distributed load from here to here, we can draw a triangle, and the area under the curve is the resultant force of this distributed load, and that force equals to 1/2 times 6 times 7.5, basically the area under the curve for this triangle, the area of the triangle, and that equals to 22.5 kilonewton. And its location is 1/3 from the base, therefore 2/3 location from the tip. And that is 2/3 of 7.5, that's 5 meters. So that's the first force. And then we can replace the second one using a similar method, replacing it by a concentrated force. Its magnitude is 1/2. Again, the area of the triangle, 1/2 times the base times the height, 6 times 4.5 meter in this case. And that equals to 13.5 kilonewton. The location is 1/3 from the base, so 1.5 meter from this base, therefore 75 plus 1.5, 9 meter from point O. So now we're ready to calculate the resultant force of this system. So the resultant force, we're assuming downward is positive, just to make things easier because we only have downward forces. And that equals to 22.5 kilonewton plus a 13.5 kilonewton. These two are the resultant forces of the two distributed loads, plus another concentrated force of 15 kilonewton right here. And that equals to 51 kilonewton. Resultant moment about point O. Again, we're going to say clockwise is positive because in this case, most of the forces, actually everything is creating clockwise rotation about point O. So don't forget we have a free couple moment here, and that is also clockwise, positive 100 kilonewton meter. And then the 22.5 kilonewton force has a moment arm of 5 meter multiplied by 5. The 13.5 kilonewton force has a moment arm of 9 meter. And lastly, don't forget the concentrated force of 15 kilonewton with a moment arm of 7.5 plus 4.5, and that is 12 meter. So in the end, this equals to 514 in the unit of kilonewton meter. Therefore, now we can replace the original force moment system by a single force, a single moment at point O, and that is 51 kilonewton downwards and 514 kilonewton meter moment clockwise. So that's part A. For part B, because the force vector and the moment vector are perpendicular, because the moment vector actually has a direction perpendicular to this plane, therefore we can further replace the single force, single moment system by a single force alone, because we can move this 51 kilonewton force to somewhere so that it creates exactly 514 kilonewton meter moment about point O, therefore replacing the original free couple moment. So this 51 kilonewton force is now replaced somewhere so that it creates the same moment about point O that is 514. And we need to determine this x bar, which is simply the moment arm. And it can be determined by taking 514 kilonewton meter divided by 51 kilonewton, and that equals to 10.1 meter. This way, we have successfully replaced the original multiple force, including distributed load and concentrated force and couple moment system, by a single force, 51 kilonewton force, placed at this specific location so that it is equivalent to the original system. It has the same resultant force magnitude, and at the same time, it creates the same moment about point O as the original system. The moment created about point O, again, clockwise is positive, equals to 51 multiplied by the moment arm of 10.1 meter. If you disregard rounding errors, this will give us back 514 kilonewton meter. So that solves this problem.